Is this working fine? Okay. Hello everyone. I hope you have had a very good first day of the workshop. So before I proceed, I just want to have a rough show of hands on how many of you are like from mathematics or physics background. 1, 2, 3. Okay. So the rest of you are all from biology backgrounds, is that it? Okay. Excellent. So so my presentations over the next few days will largely assume that I do not have a very sophisticated mathematics background, but you can plot few functions. Okay, so that's the only assumption I'm going to make. And if I'm right, yesterday Archana and others have covered some elements of very basic mathematics and plotting probabilities. So I will not be using anything more than those. And any new technique that I will be using, of course, I will be also describing that. Okay. So with that sort of requirement, so the broad topics I will cover in about 6 to 7 lectures are going to be about population dynamics and some aspects of evolutionary dynamics. So I understand that this is a workshop on population genetics. So let us just start thinking, why do we even need to study ecological population dynamics when the focus of this workshop is on evolution? Does anyone have some ideas about this? Have you thought about this question? How many of you have had some ecology or evolution background in the past? Okay, roughly half. The other half have had no ecology background at all. Okay, so those, let's say, those who do not know, I understand it might be difficult to sort of even distinguish what is ecology, what is evolution, and so on. So for those who do know, so why should we study ecological population dynamics in the context of evolution? Does anyone have any understanding of this question? Have you thought about this? Any ideas? You want to say something? Okay, individuals carry the genes and they are the ones that. Okay, so why should I study ecological population dynamics for that? Unit of evolution is population. Okay. Okay, that's a very controversial statement. Is the unit of evolution probably is population. What's the unit of selection, by the way? Unit of selection will be individuals, right? But what evolves are populations. An individual alone cannot evolve, right? So a population as a whole changes, its traits over time because of selection on individuals. Okay, so that's in some sense the simplest explanation why we do need to study how populations change over time. Okay, and that's sort of the focus of population biology, which is an extremely important subject in ecology. Okay, so yeah, with that very simple, I'm glad you sort of very nicely summarized the importance of this. So with that very sort of simple understanding, which is fairly accurate, it's really important to understand how populations undergo changes, what causes them changes, and what kind of changes can happen in populations. Because at the end of the day, what happens to populations eventually feeds back to individuals in some way or the other. Individual fitness does depend on the population that they are set in, right? So in the absence of the bigger population structure, individual fitness cannot be even properly defined. We don't know what will influence individual fitness until we know the population and the environmental structure that they are in. Therefore, understanding population dynamics is extremely important. But somewhat surprisingly and interestingly, much part of the evolution of both ecological studies and evolutionary studies have sort of happened independently. It's only very recently that people now think of what is called eco-evolutionary dynamics, where there is a continuous feedback between the ecological dynamics and evolutionary dynamics. Okay, so and now that is in fact one of the frontier areas of research. Okay, so we will of course not be able to cover the kind of techniques that is required to understand those type of models, but we will. So in my set of talks, in the first 3 talks or so, I will cover mostly simple population models, and in the next 2-3 lectures, I will cover some aspects of evolution through game theory. Okay, so let me show you this one graph from a paper that was published a couple of years ago. So these are populations of midges. How many of you know what are midges? Okay, half of you don't know. They're really tiny flies. Okay, and you often find them even on grass lawns and all in the evening times. And these are natural midge populations in some part of the world. Don't worry where and so on. They show, and what people have done is that they have measured the population density and abundance over a fairly large period of time. Okay, and they find this kind of a pattern. So as if for about 50 generations, how long do midges live? What's the generation time? Does anyone have some idea about this? So how long this should be then? Is that right? Yes. Can somebody else corroborate that? Okay, let us say we don't know. It doesn't matter. In some sense, the point of using a unit as generation instead of absolute number is that, the midge itself is not particularly important here. Okay, what's really important is how population size is changing over generations. Okay, so over 50 generations, some population has changed in this fashion. So now, I have collected this data and I have come to all of you. Can you suggest what might be happening in this system? So what are the various features of this population dynamics? So I want you to sort of, by the way, so the way I'm going to teach depends on how you interact with me. So in that sense, that I will not be able to make much progress. So tell me, what are all the interesting features in this graph, and let us see how we can understand them. So what are the interesting features that you observe in this population dynamics?
Strikingly false, and then again.
Okay, so he's saying that it's strikingly false, it kind of reverts back again. Okay, and when you say it's striking, why do you say it is strikingly falling down? Why? What makes you think so?
Within a very small time, or within a very small number of generations, it might have happened just within 1 or 2 generations. The abundance completely went down.
Okay.
Within 1 or 2 generations, it again went
okay.
down.
So yeah, that's absolutely right, and that seems fairly obvious if you look at the graph. But I also want you to, and his statement makes perfect sense only because of the y-axis here. Imagine the y-axis range was just 2, 3, 4, 5 instead of 10 power 2, 10 power 3, and so on, right? Then strikingly falling down, coming up doesn't make sense at all. Okay, so it's entirely because of the massive fluctuations in the abundances. Okay, from numbers as small as 100 in the population to as large as 10,000, and even I think maybe even 1 lakh, right? Yeah. Okay, there's a fairly large fluctuation in population sizes for a very short period of time, and this seems to be happening over and over again, right? So now, what might be driving this? I think one is the fitted line. The dotted one is the connected line of the data. The fitted one is they have used some statistical function to interpolate. Yeah, anyway, I mean, let's ignore, there is some theory and a statistical model inbuilt into it. So I will not be able to go into that. In fact, what this paper does is that it takes this data and tries to basically build a mathematical model to explain the data. So, and it turns out that to get the kind of accurate model that they have, you need a slightly more sophisticated mathematics than we are able to cover today. So obviously, I'm not going to help you explain the exact data the way it is, but the idea is to get some intuition. Okay. So let's focus. Let's ignore the difference between the solid and the dotted lines there. Yeah. So yeah, as many of you have pointed out, there are these massive fluctuations in the population sizes over a relatively short period of time. So now, what are the possible? Before we even go into mathematical modeling and so on, we want to have some ideas about what might be causing this. Okay. So can we all come up with some ideas for what might be causing this population fluctuations? Yes, you have a question. Food availability. So what do you mean by that?
When they become too much in abundance, the population, then they deplete the food.
Okay. Okay.
Then again the food becomes
So food and resources are basically changing over time. Is that what you're saying? And in a way that is roughly proportional to the population sizes themselves. But I think what you have said is slightly more interesting in that than that. What you're also saying is that these changes are actually regulated by the populations themselves, right? Okay. Okay. So do all of you understand this point? So if there had to be a slightly simpler explanation than this, it is that the food is, let's say, governed by some factors about the let's say local area where the population is present, and let us say that the time scale of the food change corresponds to certain weather changes, for example, right? Okay, and the number of midges directly depend on how much food is available in that time. Okay, that is one possible explanation. But what he is proposing is slightly more intricate. He is saying that maybe the external factors they're not changing as much as the midges really go up. They consume a lot of food. Therefore, there is very little food remaining. Therefore, the entire population will collapse, during which maybe the food will recover. So he is proposing a slightly more intricate, connection between food and and the populations, and that is making these changes. Do you think that internal dynamics can explain such a large variation in population, like orders of magnitude? Is that possible? So so that would be true when, let's say, the food recovery compares, the time scale of food recovery compares with the time scale of recovery of midge population themselves, right? So if they don't have comparable time scales, then that may not be a suitable approach, this one. So it really depends on, the time scale of dynamics of the food that the populations rely on, and what is their recovery patterns, what is their growth and recovery patterns. So you see the complexity of ecological population dynamics, right? If I want to understand this, I also now need to maybe understand what's happening to their food, resources. Are they also changing in some way? What are the time scales of the changes? Okay, and how do I go about understanding them? Okay, so there are many additional factors that one has to then think about before modeling them. Okay, so anyway, any other thoughts? Is this that those are a couple of explanations? Any other explanations that might offer some insights here? Mm-hmm. Can you just repeat your argument in a slightly more elaborate way? Cannot bring much drastic population loss, and that okay. So basically, we are proposing that the drop corresponds to the season where they don't breed and the population sizes go down, and when it's breeding season, they sort of come back up again in large numbers. Is that what you're proposing? I mean, it's possible. I cannot rule that out because in the graph there is nothing that tells me what is the time scale of seasons and how do they relate to generations, right? That's a possibility, In some sense, it relates to the comment I made before I wrote this, which is that this is intrinsic regulation of food resources. What you're proposing is an external regulation of, climatic or weather factors. Okay, what else? Predation. How can predation explain this? Mm-hmm. Why should the likelihood increase when the population has increased? Okay, but predators can eat only so much, right? Just because there are a lot of prey, that doesn't mean the predators will start eating a lot more now, right? If the 10 power 5, maybe they will eat some small fraction of it. Will that cause a collapse of the type that you are thinking of here? Yeah?
Contagious infection?
Some infection, okay. So when they are large in numbers, some infection just, so actually it's related to predation in some sense again, except that they both cause reduction in the population. Again, why wouldn't the same argument hold? There's always some level of infection in the population. Why should it be large and driving it down only when they are...
It's likely that it can have such a drastic effect with contagious and a large
Okay.
number of individuals.
Okay. Okay. So that's a very good point. So it requires what the point that he is saying requires some understanding of how diseases themselves spread. So if the population size is small and if they are sparsely distributed, infectious diseases actually don't spread too much. They infect some individuals, they also die off when the individual recovers. Okay. On the other hand, when there is a large and dense population, an infected individual before becoming recovered and immune for another infection actually spreads to some other individual. That's precisely how a lot of the diseases spread among us, especially influenza, like seasonal diseases that that kind of occur as epidemic as well. Okay, so that's a possible. So in fact, they crucially depend on the density of the population. Okay, so that's one possible explanation. Contagious. Any other explanations? Yeah.
There's non-overlapping generation would take this means that there are these midges reproduce and all die after the next. So only the larva is what is sitting, and that then shoots up this. In the next period, that shoots up, that breeds, lay eggs, and then they collapse.
Who collapses?
The current population, because it's non-overlapping population, so it will be there for the eggs which will hatch later on. It will lay the eggs, collapse, and the eggs which are laid then make the new.
So, but I'm counting only generations and generations. So I'm not counting in between. If I'm counting in between, what you are saying might be true. There are only eggs, and I'm not counting the individuals. But I'm only counting at every generation, right? Not in between.
What he's saying may be true if these fluctuations were occurring every generation, but that is not true for this.
I mean, one here, one this. There is some.
What I am saying is, can every generation collapse? After every generation, there will be a collapse because.
So we mean when you say what do you mean by, and then the next generation starts when they all hatch.
Yeah.
The generation that then I wouldn't even call the intermediate one as a collapse, no? Right? Only when the adults have come out, then I would maybe catch. So a good way to count. I shouldn't be counting X and adults and X and adults. We're only counting adults, or only be counting X. But adults are easy to count and more reliable measure. Any other explanations? Yeah. Oh my God, cannibalism? Yeah, possible. Yeah, lot of insects do cannibalize. But why should cannibalize be doing this though? Okay. They all lay off. Okay, possible. I mean, very interesting. I don't know if maybe it's worth. Maybe you can even try. Once we build the model today, maybe you can even try to modify that to account for cannibalism. I don't know how, but yeah, you can try. So density. They wouldn't see drastic drop, is it? Okay. Yeah, maybe it's worth checking if it's true. It's hard to be very sure. As we will discover today, how do these processes convert to actual quantitative dynamics is something that's not very easy to sort of make a prediction just by words alone, okay? Which is why we need mathematical models. Okay, so I mean, I'm glad you have come up with all these very nice explanations. So in my next slide, I have listed a few possible causes that often people suggest, fluctuations in the environment / resources. I'm surprised nobody said chaos, but often people say something called chaos without explaining what it is. Cycles. So because there were all these, emergence of large population sizes followed by collapse, many people see patterns in them and they think there might be some cyclical behavior in them. And I'm again surprised nobody mentioned measurement errors, but anyway, that's also possible. Some person who is measuring all these things made horrible errors. Maybe there were actually 1 million midges, but that fellow went to a wrong area to count 100 only. Possible. And not only a measurement error, but also if you do a very bad design in your study of how to count and so on, you will end up with this really wrong estimations of populations. Now, I think this point is something it's not entirely something that we study in theory as much, but if you are really trying to understand the population size in real and natural world, you will never be able to get an exact number count, right? You can only estimate the population size, and that's highly non-trivial. Okay, those can also cause these kind of issues. Okay, so and then of course we have mentioned many more interesting possibilities there, and I will add those to this list when I make a next presentation in the next workshop. Okay, so with that interesting discussion, let us see how do we go about building a mathematical model that tries to capture population dynamics that seems to show a lot of fluctuations. Of course, when we start writing models, we must not sort of extremely goal-oriented. My intention should not be to sort of, oh, I want to capture this exact fluctuation. Okay, if you start doing that, you might end up putting in some very obvious trivial factors, and you might sort of make mistakes, and you might miss out on a large, very interesting dynamics that might be happening. So it's always good to start very simple, and it's also good to start in a fairly without too much thinking about the exact pattern I'm trying to sort of explain, but maybe broadly what are the processes that we want to capture. That of course is important to keep in mind. For example, if there is a good reason to believe that these are cannibalistic, I must think how to incorporate cannibalistic in the modeling process. But in the absence of that, maybe I shouldn't do it. Yeah. Absolutely, yes. It's possible that multiple processes that are mentioned here, and along with those, might be producing the actual results. Yeah, absolutely, yes. Yeah. So go ahead.
How exactly is cycles a possible model?
I mean, this is something that one person in the previous workshop mentioned, and I don't know the exact answer, how it's possible, but maybe by the end of the day you might have some idea.
I think what he's saying is cycles is not a cause, cycles is the effect.
True, so, absolutely true, yeah. I just wrote, chaos is not a cause either, it's only a pattern, right? It's not really, neither of them are really causes per se. You're right, yeah. Was that the intention of your cause question, by the way? How can cycle be a cause? What you're observing is that, yeah, you're absolutely right. I should probably remove that from the slide, yeah. So if you were to think of characterizing the patterns, yeah, some people see cycles in them, some people see large fluctuations in them, but yeah, you're right that they are not causes per se. But I guess what they may have meant is that cyclical behavior in the environment, maybe cyclical seasonality that might be causing apparent cyclicity in the populations. Yeah, fluctuations and cycles are a bit different. I wouldn't use them interchangeably, but in a broad sense, yes. Okay, so with that short discussion, let us now think about how do we go about modeling. So some of you who have done some mathematical modeling of populations might find this, of course, very basic. So please do bear with me. So how many of you have done some population biology course in the past? For half of you, roughly half of you. So you have seen some models of populations, right? So this will be a bit of a recap for some of you, but I hope it won't be sort of entirely useless either. Okay. So how do we go about modeling populations? So when I say modeling population, I specifically mean how populations change over time. Okay. And so what are the key processes that change the population sizes? I mean, depending on how much I can actually go a bit faster, but if there are others who you think if I'm going too fast, of course I can also slow down. So just, that feedback will be very helpful for me as I, so there are, if I'm, okay, let me ask the inverse question. How many of you have never seen a population model? I mean, I want like full hands raised. Otherwise, it's very, very hard to count. Around half of you, right? Okay, so it's good that I probably go at a pace that's accessible to those who have not done this, okay? Okay, so what are the processes that change populations? Population sizes. Yeah, that can now go away. How do I do that? Is there some magic button somewhere that will take this up? Yeah, people, I mean, what are the most important and simple processes that changes? Yeah, okay. Yeah. What else? Migration, immigration, great. What did you say? What was the other term that you said? Immigration, okay, let's just distinguish. So all of you know the difference between the two. Immigration is basically, populations coming to from some other area to your area of study. Immigration is the going out. Okay, what else? Selection, okay, fine. How does, we'll discuss this a bit later, okay, yeah. Resources. Drift. Okay, what else? Age structure, okay. Anything else that are important? Okay, so what does birth and death do to population sizes? Birth will increase, death will reduce, right? So what does immigration do? Increase. So there might, so let us make a simple assumption that we are looking at, closed populations. So all of you know what's the closed population? So it's like a population on an island which is far away from any other islands, any other areas, so that I can ignore either of them. Of course, immigration will be falling off from the island into ocean or the unsuitable habitats, and that effectively becomes death in some ways, okay? And of course, there will be really no immigration per se at all, okay? So to make our mathematical modeling easy, let's assume closed populations, okay? Now, how do resources influence population size? Through competition, okay? How? What happens because of competition?
Increased competition will reduce the fitness of individuals in the field.
It will cause, sorry?
Death eventually.
Death. So, do all of you agree with him? He says that when basically resources influence population via competition, and competition is when many individuals want a limited set of resources. They all have to fight and get the resources, right? And as a consequence, it affects in, I'm generalizing what he said, may potentially a reduced birth or an increased death. An increased competition causes reduced birth or increased death. So therefore, if I were to able to keep track of birth and death carefully, I don't have to worry about this explicitly, right? So if I can modulate these two in some way, that whatever I verbally said can be captured, I don't have to explicitly track resources. Do you all agree with that? Yeah, you had a point somewhere in the back. So increase, basically clumped resources cause clumped organisms, therefore increases competition, right? Okay, fine. So by keeping track of birth and death and how it's influenced by resources, I don't have to explicitly keep track of resources. Is that reasonable? How about interaction with other species? Let's make an assumption that I am going to study only, we have a closed population of single species, which is same as saying that, which is not necessarily same as saying there are no other species. It's probably same as saying that in the trophic level there are only one species. Okay, so I don't have to worry with interaction with other species to account for competition. I do it only via resources. Okay, and for the time being, let's worry about this single population, because the more population you add and the mathematics becomes harder. That doesn't mean we should not do it. That doesn't mean it doesn't affect the real world populations. But there might be some populations where ignoring them is a reasonable approximation. Okay. Okay. So what about these three? Selection, drift. Okay. Before we go there, how about age structure? How does that influence the population dynamics? Somebody said, yeah. Who said somebody said age structure? Yeah. Okay. 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 So can we circumvent the problem by saying I will only count individuals who can reproduce? Okay. So focus only on or count only reproducing adults. Is that fine? So from now on, whenever we say population size, it's not the actual population size that encompasses all the way from across all stages of life. We only mean adults who can reproduce. Okay. Maybe it's not wise. You're right. I won't. It's a wise assumption from a mathematical point of view for the time being. But whether it affects overall results is something one can check. See, what's the wise thing to do in mathematical modeling is not necessarily very obvious. For example, ideally I want to incorporate everything in life, right? Everything that's happening to a population or an individual, I want to incorporate in the model. If you do that, what's the problem? Too many parameters, fine, but there is a very fundamental problem with that. Yeah, fine, I will incorporate them. Big deal. That's what I want to do. I like only bridges, nothing else in life. Huh? I have all the resources in the world. Yeah, you want to say something? Huh? What is the dimensionality problem?
I'm not sure about it now, but I
remember parameters and variables. Yeah, those are all mathematical problems. Let us say we can circumvent them in some ways. Yeah, that's what Nitin also said. Yeah, but I want specific systems. I like them. Huh? Sorry? Increases noise. Okay. I don't think I understood. But anyway, so, well, part of the problem is it becomes, if you add too many parameters, it becomes, you will have to rely on a very specific system, and then I cannot now, having studied midges, I will have no idea what happens to mosquitoes. I will have no idea what happens to elephants. So generalization becomes extremely difficult. But at an even more fundamental level, if I can incorporate, let's say, every aspect of a real population into a mathematical model, this mathematical model then basically becomes same as the real system, right? Okay. In some sense, it's precisely what we not want to do, because we want to understand what are the essential and important processes that affect the dynamics. But if you incorporate everything, I will not know what is essential. I will not know what is important to actually keep track of, because I have incorporated everything in it. Okay. So part of the modeling exercise, in fact, there is a very famous statement you may have heard of: all models are wrong, but some are useful. So purpose of any mathematical modeling is that we want to aim for some useful and insightful models, not necessarily the perfect model for this system. Okay. So that's extremely important to keep in mind when we are building models. Okay, so you're right. Going back to the question, is it wise to drop? It depends on what we really want to achieve from the modeling. If I do want to make predictions about midges in the next generation, it's unwise. If I want to gain general insights about what are the interesting dynamics that can happen, maybe it's wise to drop a few. And if that doesn't explain an extremely important pattern, I know that what I have missed out has something to contribute to it. And what I have included is insufficient to explain the observed pattern. Okay, so in some sense, a hierarchical approach to building modeling is extremely important to understand what's causing what. Okay, so now that leaves us only two important processes here. What do we do with them? Selection and drift. So what is selection? All of you know what is selection, right? What is selection? Will selection always drive population in a particular direction? Okay, that's a different question. Okay, let us assuming that to be true. How does that affect my population dynamics? How does selection affect population dynamics?
Like there are too many breeding individuals, but like the females are too, like the right individual, then others with
Okay, so he's giving an example of how females being choosy influences the mating and therefore the reproduction. Okay, at the end of the day, reproduction is effectively sort of summarized by births and deaths, right? Okay, now when you say selection, it's an insufficient thing to say, primarily because so many factors drive selection. Resources also drive selection, right? If the resources are limited, there is again a selection because of competition. And for example, cannibalism also drives selection. Okay, the moment there is cannibalism, individuals will develop many other strategies to evade cannibalism. So selection is always present, and that always manifests through this. So of course, selection is extremely important for population dynamics, but we must identify a specific process by which selection is acting. Okay, so what we will now do is let us assume that only resources are the important ones and other aspects are not so important. So, and anyway we are modeling birth and death, so in some sense selection is implicit in many population models. Okay, so this can we sort of therefore postpone, or or we can say it's implicit in birth and death in some sense. Or if I truly want to do, I have to say what is the driver of selection. Okay, if somebody said cannibalism, then you do include exact way by which cannibalism acts. Okay, what about drift? What is drift, by the way? How many of you know what is drift? I mean, Kavita will cover this in a much more detail over the workshop. What is drift? Okay, so I know some of you know, but those others I want to know. How many of you know what is drift already? Okay, so drift arises primarily in finite populations and small populations. Yeah, okay, and it can also occur in non-isolated populations. But what we will do in the rest of my talks is to assume that the populations are all really large. Okay, so I'm going to work in the limit of. So drift is not really important. So for those of you who don't know what is drift, it's basically the fact that birth and death of individuals are not deterministic events. Okay, so if let's say there are 50 individuals, if everyone has some probability of reproducing and giving rise to 2 children, it doesn't mean that at the when they all reproduce there will be exactly 2 times 50, 100 individuals, because it's a probabilistic event. There will be deviations from that. Okay, likewise the death is also a stochastic event. Okay, so therefore birth minus deaths will not exactly follow your intuition of deterministic approximation. Okay, there will be variations, and those variations can have dramatic influence. And the drift is a process which is the deviation from the mean expectation because of stochasticity in the birth and death. And we are going to assume a very large population size in all of our work all of the calculations I'm going to show today. So we will ignore drift entirely. Okay. So somebody had some question. I saw some hands. No? Oh yeah, you have question. Do we need to? We will come to know. Yeah. Okay. So we'll make now. So basically we will. So the upshot of all this is that we will make some assumptions about birth and death process that incorporates resources, ignores immigration and immigration because of closed populations, in some sense ignores both selection and drift as well as the age structure, because we will focus only on the reproducing adults. And maybe I can answer your question on sex ratio right away. If I am focusing on reproducing adults, who should I focus on? Males or females? Huh? Females. Okay. So as long as I assume that there are sufficient males available for mating, should sex ratio matter? No. So we will work in that assumption that, you know, we will only count not only adults but adult females. We'll assume that there are, because we are working in the limit again in this limit, whatever the sex ratio might be, there are sufficient number of males. Okay. Yes, all of you know, as you know, there are so many things that have a role to play. So let's not worry too much about all the complex processes that might be operating. Let's think of what might be the simplest, effect of resources on births and deaths and eventually over the populations themselves. Okay. Okay. So with that small discussion on what all factors and processes drive populations, let's write down some notations. Let me write this as, you know, current population size. X underscore T represents okay. So what I want to know is this. What we want to know is what will be the population size in the next generation. Okay. So where 1 unit corresponds to a generation here, and given that there is some population that is present now, and we are going to account for births and deaths mediated by resource and competition, what will be the population size in the next generation? Okay. So that's our aim. So the population size in the next generation will necessarily have those from the previous generation, right? Okay. Will everyone be alive in the next generation? No. Many of them will die. Let us assume that there is a probability D of death. Okay. So then the 1 minus D will be the survivors. Roughly 1 minus D is the probability of survival. This is the expected population size who will survive to the next generation. These are the deaths, you know, basically the survivors from the old generation. Of course, there are going to be births. Okay. Let us assume that on an average there are B offspring per individual. So that will therefore give rise to these many births. Is that right? So given a current population size, so many survived and there are now new births, and adding them up will give me new population size. Is that fine? If we simplify this, what do we get? So xt is common across both of them. We have 1 plus b minus d times xt. Okay. So so this will link the current population size to the next generation population size. Any questions on this? Fairly okay, so B is the number of offspring. Technically, you know, if you follow the thread of arguments very, very carefully, B should be not any births. It must be only female births, because I'm only counting females. Okay. And then not only that, It's a number of births that will survive to adulthood and reproduction. The number of females who will survive to the adulthood from a given female in the previous generation. It's not just the number of X, for example. There might be 100 X, but of which only 10 survive, of which only 5 are females, of which only 3 will, let's say, go to the stage of reproduction, and then in that case B will be 3, not 100. Okay. And B is for, oh sorry, I assume that 100 in X per individuals in that case. Yeah. B is defined for an individual. And the BXT is the total number from the entire population. Okay. Okay, so we have this simple formula that connects 2 generations. Let us make one very ridiculous assumption, and I will want you to think a bit more what this means. It's constant over time. If I do this, can we simplify? Oh, okay, where basically I have defined 1 plus B minus D as equal to R, and let me make an assumption that R is constant over time. So if I do that, I can write xt plus 1 as R times xt. Is that fine? Okay, and then can I, because I have assumed that R doesn't change over time, xt must have been equal to R times xt minus 1, is that right? Okay, and if I use these 2 information, basically if I substitute this in this, I can find a relationship between the population size at t plus 1 with population size at t minus 1. And what does that tell me? Xt plus 1 is equal to R square times x of t minus 1. Okay, and I can continue this process up to however long back I want. Let us say the population started off with some x1 number of individuals at generation 1. Okay. So then xt plus 1 must be equal to is this fine? So all those, I just want a nod from everybody who is who hasn't done this before, and those who are not from mathematics background. Is it okay to? Does it sound reasonable so far? Huh? So yeah. Yeah.
We're spending a lot of energy and time in this thing. So, very, very basic. This is not clear, then, my workshop will be a disaster. So, take a minute, think about this, ask questions. You have to keep that. And you need to know that there are certain methods.
So everyone is okay so far? Huh? Yeah, sure. Okay, this one. So this is, so given the current generation, so how many births happen that would stay on to the next generation? Okay, so think about it, maybe, maybe let's think of it as, two boxes, okay? This is a generation T, there are say xt individuals, okay? So total number, if I add all these dots here, will be xt, and then xt plus 1, right? There are these deaths that happen, there are births that happen, and then I wait for everyone to mature to adulthood, and then I count again how many are there. That would be xt plus 1. Okay, see, every one of them has some chance of death, and that is what the D is capturing. Okay, and then every one of these will, through birth, produce, let us say, some individuals. And say, okay, here is the thing, right? Okay, there are 2 ways to think about the problem. So one is, okay, I'm actually modeling a very complex biological system with males, females, age structure, different sex ratio, and so on, so on, so forth. And if I think of such a complex population, I have to make sure who is that I am really counting. So the XT here that I counted were not everybody in the population, because these were only adult females. Okay, okay, and the population size is always measured in adult female units. So meaning even the births must be counted only when they survive to adult females only. Otherwise, I shouldn't be really counting them. Okay, so that's one way of thinking. You know what? That's just too complicated for me. Let's make my life simple. Let's assume a bacteria-like system which doesn't have sex, which doesn't have complicated life histories. Okay, they just die, they just split, right? Very simple. I mean, they just split. Nothing else happens. I think nothing complicated happens. If you think of them, if you think of such a simple system, B just represents the, given one cell or bacteria, how many did they become? It just becomes as simple as that. So in that limit where there are no complex life histories, B represents the number of offspring from the parent. Yeah.
Can you guys tell him what is the bacteria? They start with the bacteria. What would be D?
Yeah. Okay, what would be D? What would it be? What would also be D by the way? Huh? Yeah, that fellow is not counted anymore, right? Because that fellow has divided into 2. In that simple case, D becomes 1, B becomes 2.
Then what do you expect for XT?
What will be R by the way in that case, in that scenario? R will be is equal to 1 plus B is 2, D is 1, R is equal to 2, right? So in that simple case, what would that be? This is something you may have seen somewhere, is that right? I mean, maybe you may not have seen the you would have also seen the continuous version of it, which of course I will probably try to cover that as well. Is that fine? Okay. Any other questions? If there are these small doubts, do make sure you clarify. Any?
Louder, we can't hear.
I can't hear. Oh, constant. Okay.
Being captured by the equation? Yes? Okay, so look at this limiting cases,
Yeah.
special cases. That at least helps me a lot.
Yeah, absolutely. Yeah.
When you come to the new case, which looks interesting, R less than 1.
So maybe I'll just explicitly write down what Kavita mentioned. Always, think of, limiting cases, because limiting cases are those where you know the result priori from other experiences and possibly intuition, and you want to make sure anything that you have derived fits well in that. If it doesn't do that well, either your derivation missed something crucial, or you have done some algebraic error. Okay, so it's always good to make sure it works well. So the simple case of, bacterial division, what would that be? B is equal to 2, D is equal to 1. Therefore, R must be is equal to, therefore, is that fine? And that makes sense, right? And maybe another case is, births. Birth, technically rate is equal to death rate. That would mean that B is equal to D. This implies R is equal to 1, right? When births are equal to deaths, the population must not change. And indeed, x power t plus 1 will be 1 power t times xt. That is same as xt. Okay. I'm sorry, I hope all of you can still see this, because this is an elevated landscape. Okay. Okay, good. All of you are okay here so far? And this is also called geometric or exponential growth. Okay. So let us now consider, having considered these two explicit cases. Let's now consider a case when birth rate is less than the death rate. What does that mean? B is less than D. Okay. So what happened to R in that case? 1 plus B minus D. When B is less than D, this will become negative. Therefore, R will be less than 1. Okay. So another thing always important to write, consider when you write an equation like this. Okay. The moment you have a new symbol from old set of parameter values or symbols, always understand what are the possible range of values this can take. So for example, going back to the first moment I defined R, what are the range of values that R can take? What's the minimum value of R and the maximum value of R? So I'll use this space to discuss that, okay? What's the R minimum? R will be minimum when birth is minimum and death is maximum. And D is the probability, so maximum value is 1. And B, value of B that's minimum is 0. So minimum value of R will be 1 plus 0 minus 1, that will be 0. And that means R can never be negative. Does that make intuitive sense? It must, right? Because you're having a R power something times the population size. If R is negative, this will go bizarre. It doesn't make biological sense. Okay, so R has to be 0 and above. What's the R maximum? R is maximum when B is maximum and death is minimum. So death minimum is 0, nobody dies. And B maximum is whatever the maximum offspring that an individual can have. So in some sense there is theoretically no limit, but you see the sense of it, right? It's basically 1 plus B max. Okay, so have some idea of the ranges. In this case, the upper limit is not so much, but the lower limit is very important. If you are doing some calculation with R negative, you are doing something wrong. Okay, so R is less than 1. Of course, R has to be always still be greater than 0. So in that case, what happens to this equation? In the limit of R less than 1, what happens to this? So R power T, something less than 1 power a large number will always go down. Therefore, so basically this captures, sort of population. Extinction. Okay, let's consider the other case when B is greater than D. What happens to R? R will be greater than 1, right? And you now have xt plus 1 is equal to R power tx1, and something that is greater than 1 and power a large number will always be a very, very, very large number. You can try with however small a number you want above 1, but make t 100 and you will always get a very, very massive number. Okay. Even if birth was slightly larger than deaths, you will really hit a very, very large value very soon. This means that this basically becomes a very large infinity as t goes to infinity. This sort of, there's no name for this, you can say population explosion. And in fact, it's also called Malthusian growth. Have you heard of the word Malthusian growth? It basically refers to the fact that somebody named Malthus sort of came up with the idea that when under some conditions populations can just really blow up and keep on increasing forever. Okay. Okay. So this is what this extremely simple analysis tells us. Now, what is the problem with this? So it tells me that when the births are less than death, populations go extinct. That makes sense, right? It tells me that it can help me capture the bacterial division nicely. That's great. It tells me that when the birth rate are equal to death rate, population doesn't change. It also tells me that when birth rates are greater than death rates, population sort of keeps on increasing and then it sort of reaches a very arbitrarily large value. Okay. Does this really happen in biological populations? This one, the last one. Extinction of course happens. Okay, so this does of course happen as in the bacterial growth in the initial stages, but eventually it is limited by something. Okay, and as you pointed out, it is often limited by resources that are available, right? So where did we miss out talking about resources here? You know, how do we bring the resources? I always get the spelling wrong. Okay, please you write the right spelling. I don't know. Always. So how do we bring the resources or the competition between individuals into the picture now? Where did we go wrong? No, this tells me that see, this does capture some realistic aspects, as you do know, like in the exponential phase, what is called the log phase in a very counterintuitive sense in the microbial biology literature, right? But it really is the exponential growth. But you know, it doesn't carry on forever. What about the model that led to this, but somehow is unable to capture the stopping of that phase? I assume that the birth and death rates are constant. So I assume that basically this step, R is constant over time, effectively means that birth and deaths are constant over time, or at least the difference between them is constant over time, which will be true only if, okay, so births will be greater than deaths forever only if the resources are infinite, because as the population does increase over time, that can't be true anymore, because the resources will limit the births and it will enhance the deaths, right? So to avoid this sort of, you know, an important, you know, but to sort of limit the populations that are growing exponentially forever, we have to account for the fact that R will not be constant over time. How do we do this? Shall I now, you know, basically we now know that R is not a constant. How do we incorporate that now in a mathematical modeling sense? How are we doing our time, by the way? Oh, we have 10 minutes, okay. So all of you see the problem now? All of you see why we are ending up with exponential or a Malthusian growth? We now want to limit that, right? Now we know no population will just keep on growing forever. Huh? So we just want to now understand how do we incorporate this aspect that all of us very nicely described, made perfect sense. How do we incorporate that in the mathematical equations? Say it again. Covariate. What is a covariate? Okay. How do I do that? So he wants R to be a function of something. Makes sense? Absolutely. Yes. How? Who said that? Okay. 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 Carrying capacities. How do I do that? What is carrying capacity? Yeah, what is carrying capacity? It's the maximum number of individuals that an ecosystem can probably hold, right? So how do I account? How do I mathematically incorporate it in? So all of us agree that R constant is the problem, right? That's the, if you fix somehow that, we will do that. So you're, you know, both. So two people have suggested make R function of something, and she has a very explicit suggestion that R must somehow account for carrying capacity. But how do I do that? Mm-hmm. Mm-hmm. What will be a negative number, sorry?
Like,
But we want everything within births and deaths. No, resources influence births and deaths only. Why do I want one more term? Do I really need one more term? I mean, that's one way of doing it, but is it necessary? Births and deaths are happening because of resources, right? Okay, so he is suggesting make R as a function of time. That will solve the problem, because the problem was that R was a constant over time. Therefore, one way to fix it is make R a function of time. Well, how will I make it though? Should R decay with time, increase with time? Because I don't know what will be the future population, right? Imagine a scenario when population is reducing with time. Then R will increase with time. Imagine a scenario when population is increasing with time. In that case, R will reduce with time. But I don't know what will happen in the future. So how can I incorporate that without knowing the future? Okay.
Higher populations will obviously create a competition for the resources. So say as the maximum population that the given resources can capital n. So depending on n minus x, the population will increase.
Okay. So he has a suggestion that let's make R as a function of population size itself, because in a sense R is basically effective births, right? B minus D. Okay, it's effective births. So what we are saying is that as population size gets large, that effective birth must reduce. Okay, so instead of worrying about time, so we can actually make R a function of population size itself. Is that reasonable for everyone? Meaning that the next generation, I will have a high population if we are low on the axis here. We'll have a low population in the next generation if we are on the larger side. So how should this function look like? Should it increase or decrease? Oscillate? Why should it oscillate? Huh? Oh, you didn't say, okay. You made the graph like this. Sorry? Oh, why should it go up and come down? Okay, well let's propose various alternatives. How many of you think it should just decay? Some of you think it should just decay. Okay, there are many decaying functions, we can plot some of them. I have plotted a linear decaying function, we can also have a exponential decaying function. And how many of you think it should increase? Just keep on increasing. So by the way, think what is R by the way? It's effectively now total births minus deaths, right? You are saying that the difference between births and minus will be maximum at the carrying capacity. Why? What should happen at carrying capacity? What's the definition? It's where things are, what is maximum? Size is okay, population size. But what about births and deaths? They must cancel out, right? They must not be. So R is the difference between births and deaths. So at carrying capacity, they should not be maximum. They must actually be equal to 1. Okay. So many of the points you are saying, there is nothing wrong with them. So even if I am modifying and saying, these are the comments that I often get to hear, and they are very reasonable one, by the way. Okay, so do you understand the problem? So this being carrying capacity doesn't make sense. You agree with that now, right? Okay. But now I just want an explanation why you think this is why do you want to go for this? Why do I want to have exponential growth? I just want to model the effect of resources on the population growth, right? Yeah, if R is constant, I'll go back to the current scenario. Okay? But why? And decreasing makes sense to me because as resources increase, the births and deaths difference between them must reduce, right? Okay, so reduce with time. So what? Yeah, so depends on what you're looking, but you have to explain a process that will look like, that will make R look like this. If it is just resources, I want to understand how can it be like this. So again, when you are trying to build a model, don't focus on the outcome you want to see. You must focus on the process and can you justify the assumptions of the model from the process. If resources and competition for the resources are driving population changes, does it make sense to have a graph like this? I mean, maybe there is some way it can, I'm not saying no, but it's not very obvious to me right now. In fact, there are reasons when this could be true. I'm not saying it will not be true at all, but if resources are the constraining factors, then declining of R with X is the most reasonable as approximation. Yeah. What is 0 to 1? Sorry. When you have xt 0, the population, I mean that will be accounted for by this, right? It will be accounted for by this, right? No. I mean it will be, so it doesn't matter what this number is. If xt is 0, the next population will be 0 anyway, no? Yeah. So what is R? R is basically potential births and deaths. So it's not an actual birth. The actual birth and death will be B minus R times xt. Actual births and deaths will be R times xt. It's not the, it's actually basically definition of R is in some sense per capita. If there was an individual in that location, how many births and deaths can happen? It's not the actual. The actual will be given by multiplied by xt. Right? So R is not the actual, it's the, some more like a potential. If there is nobody, obviously there will be no. Okay, so I mean, we can also discuss if you want over the break what this could mean, when this could be more realistic. But the point is that R under the resources constraints is most likely to decline with distance with population size. I'm going to write down two possible scenarios. The one is the linear decay, other is the exponential decay. For the linear decay, I'm assuming that all of you sort of have, this is xc. If xc is where the straight line intersects the 0 axis, x equal to 0 axis, then y is equal to 0 axis, then the R will be given by this. Okay. Now, if you're not sure, please go and check and derive yourself. And if it's the exponential decay, we'll have something like this. Okay. So best before we end this class, so there are of course many other possibilities. I have only written the two simplest functions that are decaying with time, with xt, a straight line and an exponential decay. Let us substitute this back into the model. What's the model, by the way? So the model is xt plus 1 is equal to R times xt. So if I assume that the this R, which is the effective birth minus death rates, reduces linearly with time, we'll have this. Okay, and if I assume more of an exponential okay, this is called the okay, so they have some standard names, useful to know. So after the break, we'll come back and continue. How do we understand them? K is some constant. So I'm sorry, I changed the constant from K to xc here. For what, sorry?
You want to give them a homework problem?
Uh-huh.
Work it out or plot
Oh yeah.
something?
Why don't you, by the time they come back, is it? Will they have enough time? Not for by. When is mine is at 2 o'clock, right? Yeah. So if we can spend half an hour and plot a few things, maybe plot. So understand, okay, here is the first thing. Write a verbal understanding of what is R. What is R defined for individuals? Is it defined for populations? What exactly is R? Okay. And then go back and plot, take these functions and plot them to make sure that they are actually these two. Okay. And then also plot the right hand side in entirety. So let us say that, let's denote the entire right hand side by f of x t. Okay. So plot the f of x t for different values of R. I'll just write the exercises. Okay, I just want to make sure. So for this very generic formulation of the model, what is the interpretation of R? I'm hoping that that will resolve some of the points that you raised. Second one is plot f of xt is equal to R0 times xt into 1 minus xt by xc for, assume that xc is equal to 1 and do this for different values of R0, like maybe half, 2, maybe 4. Just plot and get some sense. Also plot maybe, it's not very instructive to do so, but I think it's okay. I'll just, maybe this will be good enough. Just plot and get a sense of what's happening. Okay. Yeah. Also maybe I showed you the line and then I just wrote it down. Can you derive from this on your own? For those who are not very mathematically well trained, so you remember the straight line equation y is equal to mx plus c. So use that to see if given this straight line, can you derive m and c for that and then therefore get the equation back. So I will define all the points more carefully. So this will be 0 comma r0. Coordinates for this is 0 comma r0 and coordinate for this is xc comma 0. So what is the straight line that connects 0 comma r0 with xc comma 0? To find that straight line, that must be equal to this. Okay. So please do that also. That way you just get some confidence of how to write down equations from the graphs.
So please do attempt these exercises. Okay, it's very useful. You'll get really some idea about what's going on in this modeling business. Okay, so we'll now go for tea break and come back at 11:15.